Today we're talking about predicting precipitates. Specifically, we're going to do one of the practice problems from our assignment, question number 19. We're going to go ahead and do question number 19A. All right, one of the first things we need to do before we begin predicting whether or not a precipitate will form is to determine which of these ions in this possible double replacement reaction are most likely to be the precipitate. Now, we can go to our solubility rules, which we can find in the back of the textbook. You can find all that information, solubility tables, the whole thing. But here's a few of the basic rules that really are the only rules that you'll likely ever need. Here they are. I'm taking a little creative license here, but if you'll bear with me. Group 1A ions. So this would be ions like lithium, sodium, potassium, and all the other ones down that group in our periodic table. They never precipitate. If they never precipitate, that means that they are unlikely to be a precipitate in a reaction. So for example, in NaF, sodium will not be part of our precipitate because it's a group 1A metal. They're highly soluble. Now, in order for sodium to precipitate, you would have to saturate the solution so much. And we're told that these are two solutions at the start. Really, instead of saying never precipitate, we should say never is the first ion to precipitate. Anyhow, to simplify things, we're just going to say never precipitate. Next, ions like nitrates, acetates, ammonium, they also never precipitate, or to put another way, are never the first ions to precipitate. So this nitrate ion is not our precipitate. So this means our likely precipitate is going to be PbF2. PbF2 because we've got a lead 2 plus ion and we've got a F minus ion. And when a Pb2 plus and an F minus come together, this would be the ionic formula of that compound. All right, let's describe the dissociation equation for PbF2. Now that we've got the dissociation equation, let's write out our equilibrium expression. So that's Ksp is equal to the concentration of our lead 2 plus ions in the aqueous state times the concentration of our fluoride ions in their aqueous state squared. All right, so we've done all the background information. Now what we need to do is we need to determine what is the concentration of lead. Well, we were given that in the question. What is the concentration of fluoride? Well, we were given that in the question. So let's determine that. We were given in the question that we have a solution of lead 2 nitrate. So if it's a solution, we assume there is no solid. It hasn't reached its saturation point. It's completely dissociated, meaning that if we had 0.010 moles per liter of lead 2 nitrate, we have 0.010 moles per liter of lead ions. We actually have 0.020 molar nitrate ions, because there's 2 of those ions that are released for every 1 of these formula units that breaks up. But luckily, nitrates isn't really relevant here. The concentration of fluoride initially is 0.030 molar. Again, there's 1 fluoride for every 1 formula unit of sodium fluoride. So that's what gives rise to our 0.030. And this is also the initial concentration. Our initial concentration of lead ions is 0.010 molar, but when we combine these two solutions in equal volumes, the final concentration is actually cut in half, from 0.010 to 0.0050. The concentration of fluoride ions is also cut in half, from its initial concentration of 0.030 to its final concentration of 0.015 molar. All right, when we're diluting a sample, meaning when we change the volume of the sample without changing the amount of solute, there's a couple terms we just want to get straight here. First is the symbol N will relate to the number of moles of solute, the stuff you're dissolving. So in our previous practice problem, lead nitrate was the solute. The solvent was water. That's what it's dissolved in. V is the volume of our solution, and C is our concentration. Now, one thing we were told in the previous question is that when we add equal volumes, what does that mean? Well, when we add equal volumes, that means that 2 times our initial volume is equal to our final volume. So one more time, the final volume is going to be twice as big as the initial volume, because we added equal volumes. If we added 10 mils of one and 10 mils of another, you'd get 20 mils. If we added 100 mils of one and 100 mils of another, we get 200 mils. So this is what it means when we say we add equal volumes. Now, when we add equal volumes, the moles of each solute does not change, but the volume does. So let's see if we can relate that. So the number of moles of our solute initial is equal to the number of moles solute at the end. Now, let's just do a quick flashback here. Concentration is equal to our moles of solute divided by the volume of solution. Put another way, C is equal to N over V. Now, if we were to rearrange this equation, we would say that concentration times volume is equal to N. So we multiply both sides by V. We've rearranged this equation. So if we have our concentration equation where the concentration times the volume equals the number of moles solute, and we know the number of moles solute won't change when we dilute something, we end up with this equation. C1V1 equals C2V2. This is the serial dilution equation. Now you'll recall that when we add equal volumes, the final volume is equal to 2 times the initial volume. So if we sub that value in here, we should also notice that we can simplify this equation, and we're left with when we add equal volumes, we divide the initial concentration by 2. This is why we divide the initial concentration by 2. All right, let's go back to our practice problem. Now that we know why we divided our initial concentrations by 2 to determine the concentrations of lead and fluoride ions in our equilibrium system, now that we've added equal volumes, now we can plug these values in to our equilibrium expression. So QSP is a theoretical value. This is when we plug these values in, kind of a measure of the relative concentrations of each of those relevant ions. And we can solve for this theoretical value and then compare to KSP. If we think of KSP as like a solubility limit, so the KSP number for lead-2 fluoride represents how much lead and fluoride can be in solution before a precipitate occurs. When we plug in these values, we'll find out the current state of the system. If the current state of the system is greater than KSP, when we plug these values in, we've exceeded the solubility limit and a precipitate happens. If we plug these values into our expression and our QSP, our theoretical value, is less than KSP, that means we haven't yet hit the solubility limit and more can enter solution. That means no precipitate forms. All right, let's solve. 1.1 times 10 to the minus 6. We look that up in our solubility table. We're comparing these numbers. 1.1 times 10 to the minus 6 is greater than 3.3 times 10 to the minus 8. So because QSP is greater, we've exceeded the solubility limit, and a precipitate does occur. This process is pretty consistent throughout. I think all the questions you're going to see from me involve adding equal volumes. If you were ever given a question where you were not given equal volumes, you're given unequal volumes, you would need to actually use this equation to determine from the initial and final volumes the final concentration, or C2. But I'll leave that to another chemistry teacher to torture you in the future. All right, good luck. Make sure that you're kind of showing all the steps and demonstrating comprehension throughout. All right, thanks so much for watching. Good luck. Be sure to contact me. You know, like and subscribe if you feel so inclined. I've got a whole variety of different chemistry problems that you guys can review now, this term, or in the future if you happen to take another chemistry class. All right, thanks so much. Bye, everybody.